Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 7.4. I'll go ahead and read the problem statement. It says liquid methanol is pumped from a large storage tank through a 1-inch inner diameter pipe at a rate of 3 gallons per minute. At what rate in 1 feet pounds force per second, and 2 horsepower is kinetic energy being transported by the methanol in the pipe. Okay, so first we've got our tank here. It's got a bunch of methanol in it, and we're pumping it out of this pipe that has a 1-inch inner diameter and a volumetric flow rate. Okay, we're using kinetic energy, except for this is a little odd. Right here I wrote in power, right? Because we're not like throwing a ball, right? A fixed mass object. We're pumping a continuous mass of fluid, right? So we're not going to use a single amount of energy to do that. We're going to continuously supply energy to do that, right? So an energy over time, that is a power, right? So in power, right? So we're going to be using m dot. We're not going to be using m. We're going to be using a mass flow rate, not a single mass. So we're going to be working in power, not energy. Okay? Okay, so the first thing you want to do is calculate the velocity of the fluid. You have a volumetric flow rate, and you have the cross-sectional area of the pipe. Okay? So cross-sectional area of the pipe, it is a circular pipe, so pi r squared. So there's that, and that is the cross-sectional area. And then we have our volumetric flow rate. I'm going to convert that into meters, right? Meters cubed per second. Okay, so that's what that is. And then we get our meters per second velocity of the fluid. Okay, then we need to calculate our mass flow rate. So in order to do that, we need to know what the density is. The density of methanol, you can just look that up in the back of your book. And we use our volumetric flow rate, and the volumes cancel out, and you get a mass flow rate. Okay, mass flow rate. And we have our kinetic energy here. Let's start calculating that. Got 1/2 our mass flow rate times our velocity squared. Gives us this. Okay, so I could write this in watts, right? Or joules per second, but I decided to keep it as Newton meters per second. And I did that because it'll make this next part easier, this next unit conversion, right? Because we're working in Newton meters per second, it'll be easy to change our newtons into force pounds, because they're both forces, and it'll be easier to change our meters right here into feet, okay? So you just do those conversions and you get it in pounds force feet per second. And then for this next part, it's easier to have it in watts because we're going to be working in a unit of power, horsepower. So we just use our unit of power, watts, and we convert it into horsepower. Okay? Part B. The electrical power input to the pump transporting the methanol must be greater than the amount you calculated in Part A. What would you guess becomes of the additional energy? There are several possible answers. Okay, so the pump is not going to be 100% efficient, right? Nothing is 100% efficient. Okay, so what you need to know here is that some of the energy that the pump is using, if it's like an electrical pump or a physical pump or something, some of that's going to go to like friction losses, heat. It's going to like heat up the pipe or heat up the fluid. A lot of pumps will actually use the fluid that they're pumping to cool the mechanics inside of the pump. So you don't have to have like a separate coolant line, like how your computer has like a fan on it that blows the electronics off to kind of cool them down, or you have like your air conditioning unit has like a heat exchanger to pump the heat outside that you don't want. All of those things have coolants. The pump also needs a coolant, and usually it'll use the fluid that it's actually pumping to carry away some of that heat that it generates. Another thing you can have is problems with like backflow or something, depending on the type of pump you have. Like your pump is, moving back and forth, and some of the fluid that it tries to move forward, it won't 100%, push all that fluid out. Some of that fluid might get either stuck in the pump. A certain percentage of it will get recycled back into the pump on accident. Well, not necessarily on accident, but just as an inefficiency or something along those lines, inefficiency of design. And then you could also have erosion in the pipe, right? You're pumping some of that fluid, but some of that fluid is like hitting a pipe wall or cavitating or, something like that. Some of that extra energy that you're putting into the fluid is not all of it's going into actually moving the fluid. Some of it's going somewhere else. Some of it's going into the pipe or, breaking off, little minuscule pieces of, the pipe wall or, something along those lines. All of those things are inefficiencies in pumping that you have to account for when you're calculating out how much power you'll need to move a fluid. So something to be aware of. All right. Well, that is it for problem number 7.4. Thanks for joining me, and hope these problems help you out in the long run, and feel free to make any requests that you want. And I hope you have a great evening. Thanks. Bye.